So just to make sure we're on the same page, yesterday we talked about this, the measurement chain for Qbit readout. So you have some microwave source, which spits out some coherent state. It enters a cavity, interacts with the Qbit, leaks out, goes through a circulator, which prevents noise from going back to the cavity, is amplified once, amplified twice, mixed, and we obtain here in an homodyne detection, we obtain the quadratures X and P of the intra-cavity field. And we've shown that thanks to this dispersive coupling, which generate a Qbit state-dependent rotation in phase space, we can do a quantum non-demolition readout of the Qbit state. Readout which only leads to dephasing of the qubit and no spurious, in principle, no spurious qubit flips. So today I would like to look a little bit more in details about the difficulty of optimizing this readout, and in particular point out that not everything is as ideal as it should, in particular this non-QND-ness. And I'll mention one open problem of the field. So if you're interested in a research problem, there's a good one there. And so once I've done this, once I've looked at how we can optimize readout and the complexity of optimizing readout to get very fast and high fidelity qubit readout, then I'll mention other avenues to improve readout. And then I will jump to the other topic of the lectures, which was regimes of light-matter interaction. But before that, maybe it would be good to answer in a little bit more detail the question that was just asked. So the question was, okay, you have in phase space, how do you know where these blobs will end up? How do you know the separation between these two Gaussians, your two signals? And let me emphasize that how much we know about this really, and how we can really understand very well what should be the shape of this of these trajectories, if you want, in phase space. And for that, I just need to rewrite the Hamiltonian, you remember, which was describing both this dispersive interaction, but also the fact that we are adding a drive to the cavity. So remember the Hamiltonian that I wrote last time was this Hamiltonian, which was, okay, I've got some, that's an approximation, of course, because this is a dispersive approximation. I've got this dispersive coupling plus the qubit, plus you remember some drive, which has some amplitude, which could be which is time dependent. You turn on and turn off this envelope. And then there was this drive at some frequency. And what we did is that, you remember, we went to some rotating frame where it was easier to describe or to understand what goes on. And one possible rotating frame is the frame where we eliminate the frequency in the drive. So in that new rotating frame, the time dependence in the drive is simply in the envelope. Oh, and I forget now, yesterday I in fact changed this to make sure that there was an I here. And why did I do that, in fact, yesterday? Anyone can say why I did that? So I did that because I wanted this to be a P, and if in the first equation that I wrote, like here, okay, what I would have gotten is an X. Why did I want a P rather than an X? And the answer is here. Can anyone say?
To displace the two bulbs to the right, to the next.
Yeah, exactly. I wanted a displacement along the axis, and so the generator is P. There's no reason why I need this, right? I could have decided that a displacement along any axis, and in this case, I would simply draw. I could look at the marginals along this direction or any direction. Doesn't matter, right? As long as I know along which direction to look. this is fine. And as I'll argue now, I know exactly that. We know exactly that. So I just made this particular choice here because I wanted to draw the plot in this way. Okay, so there you go. I can remove that. I'll correct this, go back to a black pen. Very good. There's one ingredient that we need to add to completely describe the dynamics in phase space up to steady state. And that is what we need to add is photon loss. Okay. And how do we do that? Well, that will be with a tool which maybe was described before. Can someone tell me if the master equation was described before? I believe channels were described before, so that's essentially the same thing, but I don't know if specifically master equations were described. No, I'll assume no. We need to add photon loss. And so there's a rate of photon loss, you remember? And that will be kappa. That's the rate at which, if I put photons in the cavity, that's the rate at which they will leak out of the cavity. But how do I include this to the description of the dynamics of the system? And that's through what is known as a master equation. Here in this lecture, I cannot derive the master equation. What I can do is write the master equation and then justify intuitively why it should be like that, what it does. So if you're not familiar with this, then if you're familiar with it, fine. If it's the first time you see a master equation, I hope you'll get some intuition. And you can look at the review, for example, that I mentioned last time, where we describe this master equation in greater details. And so the main tool, as I said, is a master equation. That's the way that we add damping. And so the master equation is essentially Schrodinger's equation, but now rather than this pure state psi, is a evolution equation for the density matrix. Okay, so it's a generalization. The density matrix is the generalization of the wave function, which in addition to quantum uncertainty now can take into account classical uncertainty. And ask me a question if you're not familiar, otherwise I would assume that you're familiar with density matrices. So the first term of the master equation is very familiar. This is just Schrodinger equation now written in a different form. This is exactly Schrodinger equation, but now written for the density matrix. The new bit is this, is what we know as a dissipator. And that's something which describes losses. And the form of this dissipator is quite simple and, I hope, intuitive. It looks like this. It's not intuitive when I just write this, but I hope I can make this intuitive. So it's the dissipator with, so in the dissipator, you can put any operator here. And here I've chosen to put A, the operator which removes a photon. I want to talk about photon loss. So this dissipator which involves A, the photon loss operator. And now this dissipator looks like this. It has a term, it's a bit of a weird term, which is A, the operator that I took there, times rho, times the conjugate of this initial operator. And then this strange anti-commutator. Okay, so this is an anti-commutator. Let's get an intuition for this term. And the intuition will be to take a specific state of the field, which has exactly n photon. Okay, so let's look at what this does. But before looking at what it does, in fact, let's build intuition, right? Maybe that's better. So what I'll do is I will add a cavity, okay? And I will put some photon in the cavity, okay? I'll put some state, which I'm the only one to know what state that I'm putting in. I'll put the state question mark. And I know myself what it is, this, because I've put this photon number. And what I tell you is that I make a promise that it's that photon that I put is either one photon or no photon. Okay, I put either one photon or no photon. So my description of the state of the system, okay, my description of the state of the system is, say I did put a photon, is 1. I know that. Your description is what? The best you can say is, well, it's either 0 photon or 1 photon normalized. So that's already interesting. We're talking about the same physical system, but my description of the system, the state that I can assign to the system, is different from the state that you can assign to the system. So we have different states of knowledge about the system. Okay, it's already you can already start to ask yourself, what does the wave function describe? Does it describe the physical system, or does it describe your knowledge of the state of the system? And whose knowledge of the physical system does it describe? Okay, so your way to acquire information and improve your knowledge of the state of the system is simply to do a measurement, right? And so what you'll do is you'll hook up some measurement apparatus, a photodetector, okay? And we know the photon, if it's present, will leak out at a rate kappa. And what will you measure? Okay, what will you measure? So that's the signal as a function of time in the case where there was 1 photon, and that's the signal as a function of time in the case where there was no photon. So what you will observe should be obvious here. If there was 1 photon, at some point there will be a quantum jump. The photon will be emitted from the cavity to be detected. So you'll see a click. The detector will go click, and there'll be a signal. If there was no photon, then you will see nothing. Okay, how can you upgrade your, given, for example, that you saw this outcome, how can you update your state of knowledge of the cavity? Clearly, if you saw a click, you will declare, the state at the beginning of the measurement was 1. There was indeed 1 photon. So you can say like, okay, the state at times, I've updated my knowledge about the system, and now I know that in fact the system was in state 1. If you do not see anything, and now I'd like someone to answer this question. If you do not see anything, what are you doing? How are you updating your state of knowledge? Can someone try something here? So if you don't see any clicks.
Everybody's too shy.
Yeah, someone wants to try something. The easy answer is you will declare that it was in state 0, right? But okay, fine. But when will you make this declaration with confidence? Because, for example, if you had stopped the measurement here, you would have declared in both cases that there was in fact 0 photon, but you would have been wrong. So when are you confident that indeed it was 0? You're confident when you've waited many inverse kappa when you've waited for way longer than the typical decay time of a photon, which is the typical decay time of a photon, T kappa, is 1 over kappa. So once you've waited many 1 over kappa, you should be confident that there was no photon. But okay, fine. Now imagine that you waited for this and you still didn't see any photon. And then you waited for this and you still didn't see a photon. And this, and so I don't know, 1 over kappa is what this is 1 over kappa. As time goes on, you are becoming more and more confident that you will in fact see nothing. So you are in fact becoming more and more confident that there was no photon. So truly, as you are observing nothing, you are in fact getting more confident that there was no photon. So you should update your state of the system accordingly. The act of not measuring anything tells you that there was probably no photon. And so your state of knowledge if no click, if there was no click, should go something like, and I hope I won't screw this up, will go something like 1/2 1 minus e to the kappa t 0 plus e to the minus kappa t 1. So the probability that there was one photon goes down with time in your description of the state of the knowledge. And the probability that there was one photon increases. Fine, okay? So that's your state of knowledge as you do not record anything. So not measuring anything is in fact a measurement. Fine. So how can we make sense of the master equation now that we've said this? So that's the master equation. Remember, let me just copy this. I hope I did not expect to talk about this at all. I hope it's not too much of a detour, but I like this term. So let me continue sailing. I'm almost done with it. Good. So let's now look at this master equation and see how it generates exactly this dynamics. Okay. First, there is this term. Okay. And what is the role of this term? Well, if there were n photon in the cavity, I went a bit more general. Before I said 0 or 1, and now I'll say there's n. Well, A and A dagger acting on n does what? It brings you to n minus 1. So what does that describe? That describes the first version of the experiment where there was a click. Okay, there was a photon loss, you saw it. There's a photon loss, you saw it. So this describes a jump. That describes a quantum jump of the system, the fact that that's something that you will observe with a click. So that's a jump. That's a jump part of the evolution. When there's a photon, it will eventually leak out. What is the role of this second term? Well, the role of this second term, if there was n photons, is what? So this is, I should add the kappa here, the rate kappa. So that's kappa, n kappa, with a very crucial minus sign. So this is this. What does it do? Okay. What does this term do? Remember that this term is on the right-hand side of, remember that this is rho dot. Okay, so this is rho dot. This is how rho changes in time. This is the rate of change of rho. So what you're seeing here is that here rho, the component n of rho is changing in time in this fashion. So what is this saying is that the population of the state n is decaying with a state because of the minus at a rate kappa times n here. So what you're seeing is that the probability that there is a photon is decreasing in time. The probability that there is a photon is decreasing in time. That corresponds exactly to this no click or no jump term that we saw. Okay, that corresponds to this no jump evolution. So that the role of this term is that if there was no photons anywhere at the beginning, your description of the system should account for that. Your description of the system should say at the end, well, okay, there was no photon. Okay, and as a result, to lose photons in your description of the systems, you can do this with jumps and with no jumps terms. And the master equation adds these two contributions. Does it make sense? Any questions on this? That's a bit of a different way of introducing the master equation, but I hope it's somewhat intuitive. No questions? So why did I say that? Remember, I wanted to explain the behavior of these blobs in phase space. I wanted to understand the behavior of these blobs in phase space. And what I said is, okay, we know the Hamiltonian, so we know the unitary part, but we to this unitary part, this Hermitian regular Schrodinger evolution part, we need to add damping. Okay, and now we know exactly how to add damping. It's through this master equation, through this dissipator. And I hope that we understand intuitively why it looks like this. There's a jump term and there's a no jump term. And these play very different roles, but they match, I hope, what is an intuitive description of what goes on in the dynamics, in the dissipative dynamics. Okay, all of that being said, I can now finish the calculation of what exactly these blobs are doing in phase space. And the answer you will see at the end didn't need all of that work, but okay, we did it anyway. So now I can solve the master equation, or rather express this master equation in a different form. What I'm truly interested in is these blobs, is these alphas. Alpha if there's the qubit is in the ground state as a function of time, and alpha if the qubit was in the excited state. But yeah, I'll use a crucial property of the coherent state. Remember yesterday that I said that the coherent state is the eigenstate of the annihilation operator alpha. Okay, fine. What does that mean? That means that if I want to compute the change, the rate of change, or the equation of motion for these alpha, how do they change in time, these alphas? I can simply compute the expectation value of this, the rate of change of this operator A. So computing, obtaining alpha dot, which will give me these trajectories in phase space, is the same as computing A dot. Okay, how do I compute A dot? Well, A dot is what? Is the time derivative of the expectation value of A, but the expectation value of A is given by this. Let me rewrite it just in this way. The expectation value of A is given by the trace of A times rho. Okay, fine. So now I can write this like this. A is a Schrodinger, I mean the Schrodinger representation. So A doesn't depend on time. Rho does depend on time. But I know exactly what rho dot is, right? Because rho dot is exactly this object, okay, which commonly we write in a more compact form. I will write this as some object, which we call L, the Lindbladian, times rho. There you go. So I only need now to compute the trace of A times L rho, where L rho is this object. And that's a simple calculation to do. Okay, that's a simple calculation to do. And if you do this calculation, you will find the following thing. You will find that alpha dot, if the system is in the ground or excited state, or with my notation, I guess I should do excited / ground, is given by minus I omega r minus omega d. So now I'm just, sorry for the scrolling. If it was on the blackboard, we wouldn't scroll so much. So first, there's a contribution of the Hamiltonian, including the drive. So let me write this. And the contribution from the dissipator, the Lindbladian, the master equation, the dissipation part. So this is what I find. And I said, so upon solving this, okay, we can answer exactly the question which was asked before at the beginning of the lecture. Upon solving this, if you start in the ground state, you can write on average exactly what will be the trajectory in the XP plane, which is, remember, real of alpha, imaginary of alpha. We can exactly plot these trajectories. So if you tell me the frequency of the resonator, the frequency of the drive, you've characterized chi, you know how much power or amplitude you're putting, and you've characterized cavity damping, then you know exactly how the measurement will happen. And if you look at this differential equation, you realize that it's simply the differential equation for a driven damped harmonic oscillator, which I'll just write as. And so in the end, truly, we didn't have to do all of this work to find what we all know, the driven harmonic oscillator differential equation. But okay, we recover this, unsurprisingly, from this fully quantum mechanical treatment. Again, the crucial bit here is that in this harmonic oscillator, this harmonic oscillator takes two possible frequencies, which depend now on the state of the qubit. And this is why we have these two different blobs. Okay, so with a little bit more details than I thought, I hope this answers the question which was asked at the beginning. Anything, any comments, questions on this? I'm now moving on to another discussion, a different discussion. Okay, so let me now talk about how to optimize the readout. The qubit readout. And what are the challenges in doing this? So first, what is the quantity? When I say optimize, what is the quantity that we want to optimize? Well, there are, in fact, two quantities here. We want a measurement, which is high fidelity. If the qubit is initially in ground, I want the outcome to be ground with high probability. If it's excited, I want to see excited with high probability. And it has to be fast. Okay, so it has to be fast. It has to take, so if the fidelity, I'd like to be above, comfortably above 99% for any quantum computing applications. add as many nines as you can, 99.9999, that's what we're looking for. When we say fast, the measurement time should ideally be below something like 100 nanoseconds. We would like to be able to infer the state of the qubit in a time which is short, way shorter than what? At least way shorter than the T1 time of the qubit. Because if the measurement is a significant fraction, even just 10% of T1, then, well, in many cases, I will see spurious ground state results. If the qubit was excited during the act of measurement, the qubit will have time to relax, and I won't see the right answer. Okay, so I want both high fidelity and fast, and these two things in part go together, because if it's a slow measurement, it cannot be high fidelity because of what I just said. But by trying to make it too fast, as you will see, you can end up decreasing the fidelity also. So let me explain these things. And again, please interrupt me anytime. Okay, so the important quantity to define is known as the signal to noise ratio. And I've already talked about that when I drew these marginals, these Gaussians, and I said that there's a separation, that's a signal, and then there's a noise, that's the width of the Gaussian. So let me just formalize this a little bit more, but really we've already said the essential aspect. The key thing to remember here is what we are measuring are quadratures of the electromagnetic field, okay? Remember what we measure are quadratures of the electromagnetic field, X or P. And in fact, in practice, because of technical details that I didn't talk about, we are in fact measuring often X and P simultaneously. This is what a so-called IQ mixer does. So this signal is ours, and we can do whatever we want with it to maximize the likelihood that we infer the right answer. And the first thing that we will do is to integrate the signal. Okay, so I will define, I should have added hats here, a new operator, which I will call the measurement operator. This is really the quantity that we are measuring, and we'll be integrating for some time Tm, the measurement time. And so what this object is simply an integral of the signal, say x, with x with time, say, or p with time. I can stick maybe with the example that I gave before where the information was in the p quadrature. So let's write p here. Doesn't matter. So x or p, or in fact, both. And so we will integrate this in time. We can add to this some filter function, some additional function. And why would we do this? Well, for example, I've already said that if the measurement is too long, it's like if the measurement is T1 long, for sure I will always or almost always find the answer to be in the ground state. So this filter function can just simply say, okay, stop integrating after some time, because you know that at longer times, the answer will always be ground state. And so that's not, you're not gaining any information here. You're just gaining, adding noise essentially. And so, but this filter function can be chosen to your liking. This is your signal, you do. So this is essentially your signal. You multiply with a function of your own choice. And this is what you end up measuring. This is the outcome of your measurement, okay? And there are fancy, clever choices of this filter functions that you can make to come and enhance the signal. So now that I've said what the signal is, I'm ready to say what the signal to noise ratio is. That's a simple quantity. And again, I've already explained what it is visually. And the signal to noise ratio visually was simply, if I have these two blobs, just make sure we're all on the same page. If I have these two blobs, there was a signal, a marginal here, there was another one there. That was essentially the signal, and that's essentially the noise, okay? And so let me just write this in equations. I'll write the SNR square just because it's a little bit, because otherwise I would end up with square root of roots in a big expression. So just because I'm lazy, I'll write SNR square. And that's equal to what? If I formalize what we've said here, is pretty easy. The signal will be the measurement here up to some time t. Okay, I can decide to end at any time that I want. The measurement given that the qubit wasn't excited minus the measurement given that the qubit was in the ground state. I'll take the absolute value of this. And because it's the SNR square, I'll simply add a square here, okay? And so that, again, does represent this difference. And now I need to divide by the noise. And the noise will simply be, I'll define a noise operator in a second. So this, where I've defined the following object. Oops, I don't need an expectation value here. So this is simply this noise operator. I remove the mean from the operator. So this is essentially oops, not what I wanted to do. So this is essentially some variance here that I'm computing. Okay, so I hope it makes sense. I hope that this is exactly what you expected. So what you see is a separation between the two marginals, and I'm accounting for the noise of these two marginals. In some papers, so this is the definition that we use in the RMP in the review. In some papers, you will find expression where people just compute. Essentially, they remove exactly what I just did. They remove one of these two variances and just add a factor of 2 here. That's okay. That's a little bit more precise because in practice, the noise, for some technical reasons, practical reasons, which will come back in a second, could be different between these two qubit states. Okay, but I hope that makes sense. So now this is the quantity that we want to optimize. But what I said is that I wanted to optimize not the SNR, I introduced rather the fidelity. And you can link the measurement fidelity, which I'll call F fidelity, which can be defined in the following way. This is 1 minus the probability, 1 minus the probability that if you start in the ground state, you see an excited state, plus the probability that if you started the excited state, you saw a ground state. So 1 minus the possible errors. This can be expressed as 1 minus, is often expressed as 1 minus EM, the error, okay? And if you think about it, this error is nothing more than the following thing. Remember, we have our two marginals, which I'll draw bigger than before to illustrate my point. And I'll have difficulty doing this. Ugh. Okay, so I've got some two marginals. There's the red marginal and there's the blue marginal, and I drew them a little bit closer for a reason that will be obvious. So this is, again, that separation is the signal. the width here is the noise, and the error is what? The error is this overlap, okay? Whenever you see a signal which is in this overlap region, you cannot distinguish, you cannot distinguish ground from excited, okay? So you want to avoid this overlap, you want to minimize this overlap. And the error is exactly this overlap and can be written if the marginals are Gaussians, can be written in the following form. If the marginals are Gaussians, as we've suggested, can be written as some error function of the SNR, okay? If marginals are Gaussians, and so far they are. In the description that we've made, they are Gaussians. Practice, maybe not, but now they are. Okay, so now you see that this SNR and the measurement fidelity are really the same object. Okay, so let's focus on optimizing this SNR, which will be the same as optimizing the fidelity. Any questions? Now I'm studying a long discussion, half-hour discussion of the difficulty and the problems and the challenges in optimizing this SNR. So if there was any question about that, it's a good time. Okay. Let's now do what I just said. Let's optimize, let's consider how to optimize the SNR, which is the same thing as optimizing the measurement fidelity. And for simplicity, we will take what I'll call delta R, which is the difference between the resonator and the drive, to be equal to 0, okay? By the way, in all of the drawings that I've made so far, this is what I have assumed. If you think about this, this is the situation that I've assumed. In this case, it is easy to find an expression for an infinitely long measurement time. This is not exactly what we want, right? You remember we wanted to optimize the fidelity or the SNR at short measurement times. So it's a bit weird to be looking at infinitely long measurement times, but still that will convey a lot of the essential intuition. And so we will, that's what I will, this is what I will take as an appropriate limit to get some intuition. And in that case, you can find that the SNR, so at infinite measurement time, takes a relatively simple expression. And it's given by 2 times epsilon, the amplitude of the drive, divided by kappa, photon loss, times 2 square root, 2 kappa again, measurement time, square root. And that is multiplied by some factor, which is sine 2 phi, where phi is equal to plus or minus the arc tan of 2 chi over kappa, okay? This is what you find if you do that. Where does this expression come from? Well, it's simply just putting all of the numbers together. But at least I can say what's the intuition for this phi? And the intuition for this phi is very simple, is the following. You saw, I keep drawing these 2 blobs, which are separated in phase space like this. Well, if you compute this phase, it's exactly phi. It's exactly this quantity, okay, in steady state. So that's rho excited in steady state, rho ground in steady state. And how do you compute this? The position of the phase, the position of alpha E in steady state and alpha ground in steady state? Well, that's easy enough because you remember I gave before equations of motion for alpha dot. And if it's steady state, then you simply take this equals 0, and now you add an expression to solve. And I hope I'm not making any mistakes here and writing this expression, but I think I'm okay. So now you can simply solve for alpha excited and ground in steady state, and you can easily compute this phase. Great. Okay, we have this now. So you want to optimize. Oh, someone should say something when my handwriting is impossible to read, by the way. So reading this, I don't know what is chi and what is kappa. So don't hesitate to tell me. This should be 2 chi over kappa. So please don't hesitate to interrupt me when I'm writing foolish things like this. 2 kappa over kappa or something. Okay. How what can I say? What are the strategies now that we have this formula to optimize the SNR? Well, there's multiple strategies. One is to notice that the maximum is for chi over kappa equals 1/2. So the maximum separation that you can hope for is obtained, at least at long integration time, for chi over kappa equals to 1/2. And so in your experiment, you will adjust chi and kappa in this way. And essentially all experiments do that. The second, that statement is simply resulting from this arctan. Okay, nothing special here. Second thing to mention is that for small chi, the prefactor, so we've just maximized now the sine 2 phi. So let's look at the other factor. So the prefactor of what we've just maximized, the prefactor of 2 phi, can be expressed in the following way. And now let me know. So this prefactor here, all of this expressions I can express as 2 n kappa tm, where n is the number of photon in the cavity, n is the number of measurement photons. How did I find this? The answer is exactly on this slide. It's great if someone can tell me how did I go from 2 epsilon over kappa to saying, well, that's like square root of n. Someone can say that? Can tell me that?
Are you using the maximum chi over kappa?
No, in fact, this I've taken to be I've optimized this now. So this now I've taken this to be maximal. So I am leaving this alone. So now I'm just looking at this. And the answer is in fact this differential equation. So remember that I said this is 0. Okay, we took this to be 0 in our discussion. And I just said, okay, let's take this to be small also. Let's take it to be as small as possible. Then what you find is that alpha steady state is something like 2 epsilon over kappa. And this is exactly what you have here, 2 epsilon over kappa. But alpha, alpha square is exactly the average photon number. So there you go. This is why I wanted to give this formula. Okay, this is why we went through the master equation in the end, because I was able to tell you that, okay, this n is exactly this thing, or rather the square root of n. Great. So now we know how to increase the SNR. We just crank up the number of photons.
Alexandre, can I make a question?
Yep.
Yeah. So,
yep.
I'm mostly an experimentalist. So my question is, so the number one is a way that is mostly impacting on the design parameters of the qubit and resonator. Is that the correct statement?
Sorry, I missed the beginning of the question. So the sign here?
No, the number, no, these two ways that you have to maximize the SNR.
Yep.
So it appears to me that the number one is kind of a way that you can maximize this SNR, but impact on the design parameter of the qubit and the resonator. Is that the number two is something that can be done experimentally? Is that correct statement?
Well, yeah, so number one, this number one is really, so that's a design thing. And now here, it seems that the solution is simply to crank up the power. So here you just crank up epsilon, you just put more power. So now you've designed your experiment in this optimal fashion. And now let's just crank up the power. Yep. So this is done in situ if you want. And so visually, what we have is this thing, right? So if we have, remember we have again, we have again these blobs, which are living at some, now they are at some constant phase, right? I'm not changing this. And the only thing that we're saying is that, okay, now there is some, so now you've optimized this phase to be as large as you can. So that increases the separation. And now the only thing I'm saying is that, okay, so this is alpha, is the magnitude of alpha, which is the square root of the photon number. And obviously, if you increase the number of photon, you are also increasing the separation. Okay, so the separation, which is this, now the signal becomes that much bigger and increases with square root of n. Great. So put as many photons as you want. Unfortunately, that fails dramatically. And why does that fail? The reason, or intuitively, one reason is that the dispersive approximation will break down. My handwriting is not improving. You remember when Jens did the Schrieffer-Wolff transformation, he said like, okay, there's a small parameter, which is G over delta, has to be very small. But in fact, this is not the real small parameter of the theory. The real small parameter of the theory is rather n over n crit. And critical, this has to be very small, where n crit, the critical photon number, is delta divided by 2g squared for a two-level system. Okay, so this, please tell me if you didn't talk about this. I'm certainly did, because in one of the questions in the morning when I attended, there was a question about, there was a mention of n crit. So I believe this was mentioned. So the dispersive approximation breaks down. And so our initial Hamiltonian, right? Sorry for the scrolling. Our initial description given by this dispersive interaction is no longer valid as you increase the photon number. One thing that happens is that they are at the minimum, right? If you do perturbation theory, you should go to next order, and to next order as your small parameter doesn't become so small anymore. And so to next order in perturbation theory, you will find terms of the form new terms, which are known as Kerr nonlinearities. Okay, you will find terms that are known as Kerr nonlinearities. And the result of these Kerr nonlinearities is that, if you're familiar with Kerr nonlinearities, is that if you have some blob in phase space, okay, what will happen is that this blob, the appropriate color here is definitively yellow, because what will happen is that there's the formal term for this is bananization. The blob will evolve to take a banana shape. So there is bananization. And believe it or not, we've actually written this term in a paper. It was published and now has been written, used by other authors, something which I'm very happy with. And so clearly, if you are looking at some separation, right, you imagine that you have a blob here and now you have a blob there, but because of this bananization, you can increase the noise, you can decrease the SNR. But it turns out, in fact, that there's more going on. There's more than that going on. And we don't understand. That's the, Michel Debray calls this the skeleton of the closet of circuit theory. We do not understand what goes on. And now, unfortunately, I will need to show you a figure from an experiment which was done at ETH Zurich. And for that, I need to unshare the screen and share some new screen. So the failure modes are several, but I think I can manage. So you should see now an experimental plot. You should see breakdown of UNDness. Is that fine?
It's off screen.
Off screen. Oh, that's my fault because I. Okay. What I will do is that I will just, okay, as I said, the failure modes were many and we've hit one, and the failure mode was myself. I tried to be too fancy. So now it should be full screen, correct?
Correct.
Okay, perfect. So what are you seeing here? That's a beautiful paper by the group of Andreas Wallraff. It's a peers are applied 2017, where they really, it's one of the paper where they really worked as hard as they could to improve the SNR. And here's what they saw. So what you're seeing here is essentially the error, okay? Epsilon naught is the error at an integration time here as short as 56 nanosecond. And what you're seeing is this error as a function of the number of photons in the cavity. And look at the straight line. Okay, that's the straight line you should look at first. What you see is that in theory, the error should go down with photon number, simply because of what I've just said. The signal increases at no apparent cost to noise. Great. However, what you see, and you should see my cursor also, I believe. And so what you see are also these points, which are experiments showing, okay, the error or 1 minus the fidelity. That, okay, 1 minus the fidelity. So that label's a bit misleading. So 1 minus the fidelity, again, as a function of photon number. And you see that at about 2.5 photons, the measurement starts to go boink. something goes on, the error increases. And in that experiment, the critical photon number, I forget, unfortunately, I don't have on top of my head, was probably of the order of 100 or something like this. So you're far, far below encrypt. And despite this, there's something wrong going on. There's a breakdown of the QND-ness. Okay, and this is not understood. That's an open area of investigation. So that's a crucial data point, and that's something which is observed by essentially everyone, rarely reported. There's a few very nice papers by Jan Pop's group recently where they looked at that very carefully with a different type of qubits, and they in fact didn't see something like this. And so there's a lot of interest now. There's renewed interest in trying to figure out what goes on. Let me show you one more. No, let me skip this, in fact. Okay, I'll skip this and go. Are there questions to this plot before I unshare my screen? Okay, so we should be back. We should be back to the whiteboard. Okay. Okay. So the way to improve the readout is to maximize this phase angle by choosing chi over kappa privately to increase the photon number, but just to the limit where you start to see a breakdown. And why we see this breakdown is a mystery. Okay, so the way that you can start to solve this problem is to make the readout faster. If the readout is faster, okay, maybe you'll be able to increase the fidelity. And at least it should be faster than T1. And so the way to do that is simple, or in principle is simple. And the way it was done in the first security experiment is the following approach. And please think about why this is wrong. You have a qubit in a cavity. The qubit is dispersively coupled to the cavity. They are slightly dressed. And now what you're measuring are the photons coming out of the cavity. And they're coming out at the rate kappa. So the rate at which you're increasing and acquiring information is kappa. So what you want is the photon loss to be as large as possible. So in the first circuit QED experiments, or at least when it was realized that the readout was not optimal, was too long, people started to lower the Q of their oscillator of their readout cavity. They started to increase their kappa, and that led to problems. And I don't know if someone can understand or intuitively what the problem should be here. And Jens probably talked about dress states, right?
Yes, I think so.
Yeah, so you saw that the state of the qubit, okay, what we call a qubit state, is in fact almost a qubit state with 0 photon, plus in the dispersive regime. I always mix up this plus or minus sign. I'm sorry, I'll write plus, maybe it's a minus. Plus ground 1, okay? So the state which is actually closest to a qubit excited state has a small photon contribution. And so what happens now is that if you decrease the Q of your oscillator, well, that photon contribution, that one here, might very well decay, and it decays at a rate kappa. But what's the probability that there was a photon there in the first place? Well, it's this guy. So there's a new rate. So there's two things that can go down in this qubit. There's this guy who can go down at rate gamma 1. And now there's a photon that can also go down. And so it will go down at what rate? It will go down at the rate kappa with probability G over delta squared, the probability that there was in fact a photon in that state. And so the total relaxation rate of this dressed qubit is in fact gamma 1 plus what is known as the Purcell decay rate. Okay, that's bad because now if you keep increasing kappa, well, you keep increasing your Purcell decay and eventually it dominates. This one can start to overwhelm the intrinsic T1, and that's obviously bad. So this was seen in first experiments. So now that's another design parameter. You want your kappa to be large, but not too large. And maybe Annie will be able to talk a little bit about ways to mitigate this problem, in particular with what is known as Purcell filters, which can mitigate some of the issues associated with this so-called Purcell decay. Okay. The fourth thing to say, and the last thing, is that now we fix kappa to avoid being dominated by Purcell decay. Fix chi over kappa to 1/2 to be optimal. Then what you can find again from the equations of motion for alpha dot, for alpha, is that the steady state is reached in a time which goes roughly as 1 over chi. Okay, so the time it takes for the blobs to grow, once you've fixed all of these parameters, you find that, okay, it's the only thing which sets this time for the blobs to grow to their steady state is 1 over chi. Perfect. So now let's work with chi, which is as large as we can. There's a problem with that, obviously, because for a transmon, not for a two-level system like I'm talking about since the beginning of this discussion, but for a real qubit, for a transmon, oops, not for 4, but for a transmon, this means working at large EC, at large charging energy. What is the problem with that? Well, Jens will have told you that you do not want to have large charging energy because a transmon is a good transmon at low charging energy when the capacitances are large. And this is in this low EC regime that the qubit is protected against charge fluctuations, against charge noise. And so large EC is not a solution. Okay, so there you go. Optimizing readout in circuit QD is complicated. You need to fix chi over kappa. But kappa shouldn't be too big, and chi shouldn't be too big also. And so optimizing all of these numbers is a challenge. And there's a question which I'm happy to take. Do we consider coupling constants G always? Do we consider coupling constants G always n number independent? Chi is dependent on G, as I remember. Okay, yeah, so chi is indeed, so in the simplest case, chi is G squared over delta. For the transmon, I will honestly have to recall the formula, which I have. For the transmon, it rather reads like something like G squared over delta, EC delta minus EC over H bar, if we care about H bars here, at a factor of 2. So this is the chi that I'm saying we should not increase. It's this formula, which does involve G, as you said, but also involves EC. Here I'm not taking any dependence on n. So I hope that's answering the question. Please don't hesitate to ask any questions. So if we go back, so the thing is that optimizing is challenging. But that doesn't mean that it cannot be done, right? Building a quantum computer is a challenge. So that's fine. Challenges are what we are up for here. And so the state of the art is quoting the paper from ETH that I mentioned before, the one which saw this upturn at low photon number, was that this fidelity was of the order of 98.25% in a measurement time of 48 nanoseconds. So very short measurement time, in fact, with respect to typical measurement times, and 99.2% in TM equals 88 nanoseconds. So if you allow for more time here, more integration time, you get more signal, and therefore you can assign with higher fidelity the state of the qubit. This was done, as I said, with 2.5 measurement photons, much farther than encrypt. And that's very unfortunate. We still have to understand that. And the main limitation was that the T1 was something like 7.6 microsecond. That's a very short T1 with respect to state of the art. So that's a paper from Walter et al. PR applied 2017. Okay, so other groups have optimized the readout since then, but this is the one which really does the best job at thinking about this. And so, for example, if you use the IBM Q machines, which are online, you'll find that their readout is done not in nanoseconds, but I believe something from 2 to 3 microseconds, and with similar or worse assignment fidelity, readout fidelity. So this is not something which is trivial to do, but again, can be optimized. I'm done with talking about dispersive readout with this. I'm happy to take any questions or start something else. Or it's time to take a break. I think there's 15 more minutes, but we can stop for questions. I don't see any questions. So let me.
Yeah, so the break is, I think, is 10:45, but feel free to, if you think this is a good moment. Yeah.
No, but there is before moving to the next topic, there's a few comments that I can make, which are still about readout, and will maybe be interesting for other topics we'll be describing in school. In fact, so what I'd like to talk about is other approaches to readout. To qubit readout. Here I wanted to spend more time, but I'll limit myself to the next 15 minutes to be able to move on to the next topic this afternoon. Well, in the next set. And the first question that I would like to ask is, would squeezing help? Could we use squeeze radiation to improve qubit readout? And I imagine not everyone is familiar with squeezing. So I can say a few words about that very briefly. It's simple. And then I will move on. Maybe I can say that how I came to think about this question is interesting. So many years ago, in fact, the first PhD student that graduated, that got his PhD in my group, Steve Gervin was on the evaluation committee for his thesis, and he couldn't be there, so he sent his question in writing. And one of the questions was exactly that: would squeezing help? And this is something that we had discussed before, and I felt I knew the answer. But when I saw the question from Steve, so if anybody knows, Steve is a like super bright guy, and so I said like, okay, this has to be a very deep question because it's coming from Steve. So let me think carefully about this. And I started thinking and realized that what we had been saying, in fact, colloquially in the always of conferences in the field was wrong. Squeezing would not help, as we will find now, would not help dispersive readout. And so I came back to Steve saying like, wow, that was a great question. I didn't really think it through, but now I understand that it doesn't work. And his answer was, oh, this is not what I was thinking about. I was just thinking about our usual way of using, that we thought that we could use squeezing. So that's an interesting thing, I think. If you think someone will ask a deep question, you might be tempted to find a deep answer. Well, not so deep, but think at the answer more carefully. So what is squeezing? What is squeezed radiation? And that will come back again. And maybe LIGO was described the first few days, and therefore squeezing described.
No, it wasn't, Alexandre.
Okay.
So it's important.
I'll say just a few words, but there's a lot to say about that, of course. I'll give you, I won't do the mistake yesterday and starting to talk about coherent state when I was not ready to talk about that. And mostly what happened is that I started to talk about coherent state and realizing, oh, there's a much better way to say this. Now, how do I go from what I'm saying to the much better way? So here I will keep it simple. What we saw so far are things like vacuum state, or so vacuum, and displaced vacuum state. Okay, so alpha. And in both cases, what we have for the states is that delta X, delta P saturates the Heisenberg inequality. For the quadratures that I defined before, that's 1/4. Okay, and obviously this could be bigger, but not smaller than 1/4. But that doesn't mean, however, that the delta X has to be equal to delta P. You can, in fact, make the noise in quadrature as small as you want, but this has to be compensated. If you crank this one down, this has to be compensated by the other quadrature whose noise has to increase, such as to still respect the Heisenberg inequality. And that's squeezing, that's squeeze states. And the word squeezing comes, I believe, from Carl Caves, who said you will take a vacuum state and you will squeeze it. Oops, now I'm drawing a straight line. So if this is vacuum, a squeeze state will look like this, where there is an uncertainty delta X, an uncertainty delta P. You still have delta X, delta P equals 1/4, but delta X is no longer equal to delta P. Let me make sure that I have the expression okay here. So yeah, okay. Good. So you have delta x, delta p. Yes, perfect. Okay, this is what I was looking. Now, this is given by, let me erase this. So this is common to introduce a parameter, which we will call r, such that this becomes e to the minus r, while this becomes e to the plus r. And r will be the squeezing parameter. Okay, you can, in this way, give the squeezing parameter. Excellent. And sometimes this squeezing will be described in terms of dB, how much decibel of squeezing there is. And the way this is done is simply by comparing the noise in a squeeze, or so there is a squeeze quadrature here, and there's an anti-squeezed quadrature. So you want to compare the noise of the squeeze quadrature to noise of vacuum. And that comparison is sometimes given in decibel. The larger the squeezing, the more decibel they are. The more decibels of squeezing they are. Okay. Of course, you can also have displaced squeeze states, right? You can have states which are displaced and squeezed. That's also fine. Excellent. By the way, this is called sometimes quadrature squeezing. Because if you think about it, there's other quantities that you can squeeze. You don't have necessarily, this is usually not discussed in this way, but I can mention it, I think. Here I'm squeezing X, I'm squeezing P, but sometimes when talking about photo detection later for axion detection, it might be useful to say that there's other two conjugate quantities that you think about, which are the photon number and the phase. And a Fock state, you can, in some sense, think of it as a state in which you squeeze out all fluctuation. So it's a number squeezed state. Okay, we won't really use this terminology here, but you can if you want. So there you go. So this is a squeezed state, a state in which delta X and delta P saturate the Heisenberg inequality. The area is the minimum allowed by quantum mechanics, but X and P don't have the same amount of squeezing. There are also squashed states, and that term squashed is used when delta X, delta P is not saturated, but still there is some squashing of the state. The state is not, the noise in X is not the noise in P. Okay. So how could we think that squeezing could help? Well, it helps, we could think, because what we have is this, right? So what I have is the two blobs, which are rotating in phase space, and the two blobs are here or there. And now what I want is to maximize the signal to noise ratio. And there's a simple way to do that, right? I can maximize the signal to noise ratio without changing the signal, simply by changing the noise. I could imagine, for example, squeezing along the P quadrature. And in this case, that's great. I've improved the SNR by squeezing the noise in the P quadrature. So this is what we want. However, the story is simple. So what really happens? So remember, the Hamiltonian will be rotation. The Hamiltonian for the dispersive readout will be rotation plus displacement. Okay, I have chi a dagger a sigma z, oops, z, plus this drive. Okay, and now what I'm assuming is that I will be starting with a squeezed vacuum state. So, okay, instead of starting with a vacuum, pure vacuum, I start with a squeezed vacuum state like this. And what I would like is to have an evolution which looks like this, where now at the end of the evolution, the two squeeze states are like so. But unfortunately, this term, as we said, is a rotation. It rotates the center of the blob, of the coherent state blob. But unfortunately, it also leads to a rotation of the squeezing angle. If you do the math, it's easy to convince yourself that what will actually happen is more something like this. And if you start here, okay, you now there's a evolution like this. What happens is that you will end up with, maybe my rotation is over exaggerated, but that's the idea. And my states are no longer very squeezed, but okay, you get the feeling. What you have is that there is a rotation of the squeezing axis, and now the noise is in fact larger. The noise that you were hoping would be smaller is in fact much larger because of this, of the contribution from what I call the anti-squeeze quadrature. Now the anti-squeeze quadrature is in fact contributing to the noise. That's unfortunate. Squeezing doesn't help. That might be counterintuitive for those who know anything about sensitive measurement, because typically when I want to measure a phase, and that's what I want to do here essentially, right? What I want to measure is this phase. Do I have plus this phase or minus this phase? So you would think intuitively that a problem like this would be improved by the use of squeezing. The key thing here is that squeezing helps, but in a very specific case. It helps LIGO, for example. I hope this will be described later. It helps LIGO because the phases that are measured are very small. The phases that are measured are very small. And so if the phase that I was interested in was very small, I would end up with a very small rotation of the squeezing axis. And I would end up having pretty much what I wanted. So if I was after measuring a tiny phase, it would work. In practice, however, measuring a tiny phase will be very difficult. This will not improve. If you look at the maths, you find that there's no way that this tiny phase, despite the fact that the noise is now reduced, right? The signal is so weak that despite having a small noise, you will not really gain. So squeezing helps in a phase measurement when the phase is very small. And so for those who are familiar, for example, with Bernie Yerke's paper, moving on to a little bit more technical things, but if you're familiar with this famous SU211 paper, you will find beautiful expressions for how squeezing helps, but every time there are limits of small phase taken. Here, we're not interested in this limit, thereby squeezing does not help. Okay, so that was a long story, but I think it was important anyway to introduce this concept. It was important to introduce this concept.
There is a question, Stefan. Maybe you want to speak?
Okay. Yeah. Okay, well, you can ask your question.
yeah,
I can read it if you want. Whatever you prefer.
Yeah. Well, so my question is just, I guess here in your plot, you're still assuming that we are like measuring the vertical quadrature, right? The P quadrature, I think it is.
Yeah.
If you had a way to like directly measure phase and not measure amplitude at all, then here you're still like just you're squeezing along phase. So if you really would measure phase, I guess it would still help. I don't know if there's a way to do this at all. So that's my question.
Yeah, so that's a good question. But in practice, we can measure phase, but this is always reconstructed from quadrature measurements. So we have what we have are linear detectors that detect quadratures of the field. This is what homodine detection does. And what you have is indeed X and P. And from this, of course, right, once you have X plus IP, you can reconstruct amplitude and phase, but they are reconstructed from these quadratures. You would have to think about different types of detectors, and there are different types. So tomorrow we'll talk about single photon detectors that are only sensitive to this quantity and not this one. But yeah, I don't know of a detector that would only give me access to this. That's an interesting thing to think about, in fact.
Yeah, I was exactly thinking about the single photon detectors, which give only access to A. So I was also wondering if there is something, but
okay.
Yeah, thanks for this answer.
Is there any other question? Okay, so if not, we take a break.